So now reviewing this updated simulation, this is looking pretty cool, but it's still behaving fairly erratically. I'd like to get a bit more of a nice flowing motion through these tentacles, so let's take a look at perhaps applying this turbulent wind in a slightly different way. And also, these curves look like they're doing some sort of collisions with each other, but it's really hard to evaluate when we're just looking at curves here. So let's first go ahead and set up a deformation for the actual creature's tentacles so that we can get a better idea of what this really looks like on some thicker solid geometry. So going back into our network here, we can perhaps wire in this creature that we've already merged in, or just to keep our scene a little bit cleaner, I'm just going to copy that creature, and we'll paste a copy of that down here after our vellum hair curve solver. And then we're going to, instead of just using a blast to isolate the tentacle sections, I'm going to change this to a split instead so that we can display this with the rest of the body as well if we'd like. So on this blast here that's isolating those tentacles by the path attribute, let's just cut that path attribute group there and delete the blast SOP, and I'm going to drop in a split instead, connect that to our object merge, and paste those paths back into the split group here. Now if you display that, that'll just show us the tentacles. So if we invert that selection, then in the first output, we'll get the creature body here. So we can just drop in a null, attach it to that for clarity. I'll call this body only. And then for the second output, that's going to be our tentacles, and those are going to get point deformed by our simulation. So drop in that point deform and connect our tentacles to that. And then we're going to use our curves from the simulation to deform the tentacles, but it's not going to work very well if we just use the curves directly. We can take a look at what that looks like. We can, for the rest point input on the point deform, connect that up to our curves from before the simulation. And let's drop a null for reference there. This will be the rest position. We'll drop another null for the deformed, and connect the deformed null to the simulation output. So we have our rest curves, and then we have the deformed curves as our simulation output here. Put that into the third input of our point deformer, and let's see what our tentacles look like. And you can see here that these are not deforming very nicely. The point deformer doesn't play as well with curves as input as it does with meshes. So a quick fix to this will be to do a polywire to just create some simple tubes along our simulation curves here. So let's just drop in a polywire. Just put that before the deformed null first, and this is creating a pretty skinny polygon tube here, which is actually fine. We don't need these deformation tubes to be as thick as our tentacles are. It's totally fine, and perhaps even a little bit more effective for them to be fairly skinny. Although I'm going to make them a bit bigger than this, and I'll try a wire radius of 0.5. We don't need much resolution around them because these are just being used as deformers. And to make sure that the rest position matches the topology of these deformed tubes here, I'm going to go to that polywire and create a reference copy of it. So right click, actions, and create reference copy. And we'll drop that onto the rest position null here. And now if we take a look at our new point deform results, this looks correct instead of that weird result that we were getting before. Now this still doesn't look as nice as we want it to. We're going to fix some things here. There are some weird things happening at the roots of the tentacles here. I mentioned before that we were starting out by just pinning the very first point in place, but we may need to pin a few more points because you probably don't want this section that the tentacles are attached to be quite so weirdly deformed like this. So let's change our pin group now, and let's go up to that group expression where we're setting the pin group. And right now it's just grabbing that very first point on these curves. Hopefully that's not too hard to see. And let's template display the creature geometry so that we can see how many points we want to pin in place on these curves. So with that template view on those creatures, it looks like we want to pin points up through approximately here. So on this group expression, let's change this p.x threshold value. So let's try something like 15.5. That only gives us one more additional point, so let's increase this a bit more. It looks like 19 will also include the very first of these tentacle ridges, which is just fine, especially because we might be doing some smoothing on these curves afterwards. So you might want to pin in place an extra point or two beyond this connection point here, but we can finesse that some more as we do some updated sims and see that applied to the tentacle geometry. And I had also mentioned that the overall behavior here is pretty erratic, and this pop wind can be pretty effective for applying just turbulent wind like this, but sometimes if you want a lot more control and visualization over what this turbulence looks like, it can be much more effective to use a velocity volume to control this turbulent wind instead. So let's drop in a bounding box to use for this volume velocity. So just type in bound to create that bounding box, and let's connect that to our tentacle curves that we're bringing in. And then we're going to want to scale up this bounding box quite a bit. We want to make sure that it's large enough that it can fill up the entire space that these tentacles might reach when they start flying around. So we can increase the padding on this bound SOP, or we can also just use a transform SOP, and I'll use my centroid transform preset, which will just give us a pivot at the center of the object, and then we can scale up from that. So I'll try scaling this up on the y-axis by 5. Let's display that transform. I'll scale it up by 5 and the z-axis as well. And then in the x-axis, we can maybe scale it up not quite as much because we don't expect things to be flying very far on that x-axis there. Let's try 1.2. Maybe display our curves once again and template display this bounds that we've set up. And we can also use a combination of this transform SOP and the bound padding. So perhaps on this x-axis, we want to give ourselves a little bit more room on this positive x point here. So I'll just add some upper padding to the x-axis there on that bound SOP. And this looks like it should work pretty well. So now if we drop in a volume and name this vel for velocity, make sure to change the rank from scalar to vector, because velocity is a vector attribute, it's not a single value. And now we can use a volume velocity SOP to add some curl noise. So drop in that volume velocity, go to the curl noise tab here, and turn on add curl noise, and display that. And now when you display these velocity volumes, sometimes this information won't really look like anything sensible, because this fog display for velocity is just not a very helpful way to visualize a vector attribute like this. It's not really telling us much about the actual directions of these velocities. And it's also quite low resolution. You can tell that this is a very low res volume right now. So on this volume here, let's turn up the uniform sampling divs. Let's try 150 divisions on the max axis. And then to visualize the actual velocity directions and to see what the curl noise really looks like, let's create a volume trail for this. And this is going to visualize the velocity direction based on some points that you've input. So I'm going to drop in a pyro source, and this is a fairly large scale box. This is over 100 units long, so this particle separation of 0.1 on the pyro source will create lots and lots of points, much more than we actually need. So let's turn the particle separation up to 1 and connect that to the transform, which is just a polygon representation of where that velocity volume is. So if we display that pyro source, you see it's only giving us the corner points of our input by default, because the pyro source mode is just set to keep input. But if we flip that to volume scatter, that will fill this input volume with points. And now that we have this volume filled with points, and we have a velocity volume here, now we can visualize those velocities with the volume trail SOP. So drop that in, and the first input will be the points to trail, so connect that to the pyro source. Second input is the actual velocity volumes, so connect that to our volume velocity here. And then if you display the volume trail, this is going to show us the actual directions of all of these velocities. And this is looking very crazy. It's super high frequency detail right now, but as we increase the swirl size on our volume velocity curl noise, then we'll get some much more interesting shapes out of this. So turning this up to 10 gives us some nice recognizable swirls there. And for this, you might want to display the actual creature mesh as well, so that we can see what these swirl sizes look like in relation to the size of the creature. And I'm going for some fairly big flowing features with this noise. So 10 still looks kind of small scale. Let's turn the swirl size up to 20. And that's looking pretty good. I like that size for now. And you can feel free to flipbook this velocity volume as well if you want to get a sense of what the evolution of these shapes looks like over time. But another consideration is that sometimes in cases like this, I want there to be a turbulent push on the y-axis and a push on the z-axis back and forth like this, but I don't necessarily want a big turbulent push in the direction that the wind is flowing. So I'll often want to just turn off the velocity amount on one axis. So going back to our volume velocity here, let's right click on that output and we'll drop in a volume wrangle. Make sure this is a volume wrangle, not a point wrangle or an attribute wrangle or a primitive wrangle or anything like that. The volume wrangle is a bit different. And then in the vex, we can type @vel.x equals 0, and that will get rid of the x component of the velocity. So you can see that now our noise is only going up and down and side to side. It's not going back and forth along the length of those tentacles, but I am still going to apply some wind direction in this velocity volume as well. So instead of setting this velocity x to 0, let's set this to 1. And then you can, of course, change this value here in this wrangle to control the strength of that wind direction relative to the strength of the turbulent noise. So you may want to tweak that a bit. On this volume wrangle, I'll just rename that to wind direction velocity. And with that change, you can now see that we have our velocities all traveling on that x-axis, but being pushed around by that turbulent curl noise. And one mistake that's very easy to make is to reference this volume trail SOP in the DOPNet. So if you try to take the output of this volume trail and use that to advect your simulation points, then that's not going to work because this volume trail is just a polygonal representation of what the velocities are doing. You have to make sure to actually pass in the volume itself, not the volume trail output. So let's create a null for that volume velocity reference, attach our wind direction velocity wrangle to that, and I'll call this wind volume. And now if we dive inside our Vellum solver, we can disconnect the pop wind there because we don't need that anymore. And instead we're going to use pop advect by volumes. Connect that to the force output. By default, this is looking for a field named vel, which is what we've named our velocity volume, so we don't need to change that. We just need to point this SOP to that volume that we've set up. So let's open up our selector and then find our wind volume reference null there. And because we're working at a slightly large scale here, this velocity scale of 1 is going to be a very subtle influence, which in some cases might be fine, but we want a much larger and more noticeable influence here. So I'm going to crank this velocity scale up to 50. And now that we have this new method set up of applying our turbulent wind noise, and we've done a point deformation to actually see what this looks like on our creature geometry, let's now do a new simulation and check out these results. And now checking out our updated simulation, this is looking really cool. There is still a bit more frenetic energy happening in here than I would like, so we can tone that down a bit. And it does look like perhaps the tentacles are getting stretched out a bit. I actually don't really mind the tentacles getting stretched out a little bit. It doesn't really bother me, but you can see that they are ending approximately right here at the rest frame, but then by the time it gets to the end of this simulation flipbook, they're going off the edge of the flipbook a little bit here. So they are getting stretched out quite a bit, and of course we can address that stretching out a couple different ways. We can try cranking up the stretch stiffness on the vellum hair constraints here. So maybe I'll try turning that up to 100 on this stretch stiffness here. And if that doesn't do the trick, you can also try turning up the constraint iterations, because that's a bit more of a brute force way of enforcing constraints. And I often find that this can be a bit more powerful than just the constraint settings themselves. But in this case, we'll see if cranking up that stretch stiffness value does the trick. And it's kind of up to you aesthetically how much stretch you're okay with in these tentacles here. For me, it doesn't really bother me. For this sort of frenetic behavior that's happening in here, one thing we can do to address this is to apply some velocity damping to this. So if we go back to our Vellum solver here, and then go to the Forces tab, we have this velocity damping control. So in this particular case, I want a kind of smoothly flowing tentacle look here. I don't really want this to be super energetic. So I'm going to try cranking this up quite a bit to about 0.8. So let's see how this is behaving with the increased stretch and the cranked up velocity damping. So now this updated sim is still looking a little bit energetic at the beginning of the simulation, but oftentimes the beginning of a sim, particularly with deformable sims or character simulation, the beginning of the sim can look a little bit strange. And with many types of deformable sims, it takes some time for things to kind of relax into a natural behavior. So this is why you'll often see a whole bunch of pre-roll frames being simulated before the actual start of the shot. And in this particular case, we kind of know that we're not going to use the first 50 or so frames of this sim. It's not until after around frame 50 when things start looking nice. So we'll just make sure that whatever time offsets we use only start from frame 50 onwards. So I wouldn't worry too much about some poor behavior at the very beginning there, as long as it kind of settles out nicely toward the end. And this is looking pretty good. Things are flowing pretty nicely now, and I'm liking this behavior. The stretch actually looks a little bit worse now. This could be because the velocity damping is, perhaps reducing the ability to compensate for the stretch or something. But in any case, if you don't like this stretch or you get notes on it, we may need to either crank up the stiffness a whole lot more, or we can try increasing the constraint iterations, which, as I mentioned, can be a more powerful way to enforce constraints at times. Because this is getting stretched off the screen a fair amount by the end there. And it does kind of feel like there might be a fair amount of friction between these tentacles, and I want these metal tentacles to kind of smoothly slide across each other. I don't really want them sticking to each other at all. So I'm going to try reducing the static and dynamic friction thresholds. So going back to our Vellum solver here, on that Forces tab, you can see static and dynamic friction thresholds here. And these are multipliers on the friction attribute if you have one on your Vellum object. If you middle mouse on our Vellum hair here, we don't have any friction attribute, so it's just assuming the friction to be 1. But I really don't want much friction at all between these tentacles, so I'm going to reduce the static threshold from 0.5 to 0.05 and the dynamic from 0.1 to 0.01. The difference between static and dynamic friction is because when you have two objects at rest, it takes more force for them to start moving relative to each other than when they're already moving. Once they're in motion, the effective friction between them is a little bit less. So we've reduced that quite a bit. Going back to the Solver tab, we can try cranking up our constraint iterations a bit here. And then going back to our flipbook, let's take another look just to check how our collisions are doing, to see if we have a lot of interpenetrations or not. And as I've mentioned before, some amount of interpenetrations between tentacles isn't necessarily problematic because you might not notice it in motion, especially rendered with motion blur. But if there's quite a bit, we may want to do what we can to minimize that. And it doesn't look too bad, but it does look like in some areas we are getting perhaps a fair amount of overlap. Yeah, we're seeing perhaps a little bit in here, but it's actually looking pretty good. I'm not too worried about it. We can always add a little extra collision buffer back on our Vellum hair settings with our edge length scale control here. So if we display that and take a look at that thickness, we can perhaps increase this a little bit more. Maybe I'll try something like 3.3, which is going to be a little bit fatter than the actual tentacles are, but because they do seem to overlap a little bit anyway, this may help to enforce those collision behaviors once they're applied to the full resolution mesh. Maybe that's looking a little bit too thick though, they're kind of overlapping a bit. Looks like a value of 3 is a little bit more reasonable and avoiding overlap between the tentacle curves. And now with that increased collision thickness and increased constraint iterations and reduced friction, we can do another flipbook to see what our latest updates look like. And now finally, I'm quite happy with our end result here. It looks like the stretch in the tentacles isn't too bad since we've tamed that with those constraint iterations, and the overall behavior is looking pretty good here. You could potentially extend the curves a little bit further so that they reach the tips of these pointy ends here, because right now our curves are actually only going up to the base of these pointy sections here. So we could potentially extend out the curves to go all the way to the tip of these pointy sections if you want this entire section to be covered by the curve, because right now, because our curves are ending at the base of this cone, there's actually going to be no collision between the cone tips, and I don't think it's terribly obvious, but if you do find that it is obvious in your shot, then you might want to extend the curve a little bit longer to take up the full length of this all the way to that sharp tip there. But playing through this in motion, I think it's fine. It is looking perhaps a little bit energetic, but we can also control these things post-simulation as well if you want to. So one way that we could quickly retime this post-simulation is if you type in time warp. that will create a retime SOP here, and we can drop this after our simulation. And typically you would want to do this after you cache out the sim so that you don't need to run a new cache every time you want to time warp this. And then if we go to frame 1 of our sim, we could set the input start frame to frame 50. So at frame 1, it's actually going to be grabbing frame 50 of the sim, and then by frame 100, it's grabbing frame 100 of the sim. And we can tell this to pre-extend and post-extend that range so that this same speed remap will happen before and after our input there. And let's turn on interpolate between input frames, which is totally fine to blend between them in this case because the topology of our curves is always the same on every frame. And now we can once again flipbook this and see what the retimed version looks like. And now playing this updated retimed version, you can see now we've drastically affected the overall feel of this simulation. This feels quite a bit closer to what I'm actually looking for here. It's a much smoother and more ethereal motion. So depending on what you're going for artistically, this retiming technique can be extremely helpful in situations like this. I am noticing the collision issues a little bit more as things are slowed down, because when things are moving around really energetically, you don't notice these issues nearly as much, but certainly when things are slowed down this much, some of these things become a bit more apparent, like all of these collision intersections in this area here. So a couple things we can do to fix that are to perhaps increase our collision steps, and we could potentially increase the overall number of sub-steps as well. And while we're at it, I think I will fix the issues where the curves don't go all the way to the tips, because I would like us to have some actual proper collisions all the way to the points of these tentacles. So let's template display our creature geometry here and go back up to our curves that we have as input here. And I'm going to copy the group expression that we used for our pin, and I'll paste in that copy just before the existing pin group expression. For the new one, I'm going to set the group name to endpoints. And it looks like our maximum x value is 84.07. So in the vexpression, I'll check to see if p.x is greater than 84. And let's display that endpoints group there. And then if we zoom in on it, you can see that is correctly selecting only those very endpoints of these curves. And another way that you could select start and endpoints of a curve is to use the group by range SOP. So if you connect that to our tentacle curves here and display that, and we can change that group type to points. The range type is going to stay relative to start and end. We can set the start and end equal to 1. And if you select invert range, that will just give you a single start and end point. You can see we've got 1 point selected there and 1 point somewhere else. Yeah, all the way over here. But that's not very helpful because we want start and end points for all of these curves. So if you go down to this connectivity section of that group by range, you can turn on Affect Disconnected Geometry separately. So if you turn that on, that will give you all of the start and end points for all of the curves, which hopefully is not too difficult to see in the screen capture here. But that's selecting all of those start and end points. And we can disable the start points just by setting the start parameter to 0. So now we're only getting all of these endpoints here. And actually this is slightly more slick than using our group expression. So I'm going to just stick with the group range option instead. Let's delete our group expression for the endpoints, drag in our group range instead because this is a slightly more clever and procedural way to do it. Set that group name to endpoints, and I'll drop in a soft transform. And the soft transform group will select the endpoints, then display the soft transform and increase that X translation until the points reach the very tips of these cones here. And now let's get rid of our template display of the creature geometry just to check out the spacing of the points. Because for our curve simulation here, it will likely behave more nicely if we keep the point density consistent. So there are a couple things we can do to ensure this. On the soft transform, we could increase this soft radius here. Because these are pretty long curves, we can probably use a rather large value for this soft radius. Try something like 50, and I'll set the soft type to linear. Kind of a subtle difference, but linear seems a bit safer to me. You could also instead do a resample. So if you drop this after the soft transform and display that resample, you can see by default this is adding tons of resolution to those curves. And you can change the length parameter on this resample to get just the amount of resolution you want on these curves, which could potentially be a helpful way to control your simulation results as well. I'm just going to stick with the soft transform for now, but I'll leave the resample in the scene just because that's a helpful option as well. And now to improve some of these collision issues, let's try cranking up our substeps a bit and our collision substeps. So back on the Vellum solver, I'm going to set the collision passes to 50, and let's turn the substeps up to 10. And now going back to frame 1 is actually cooking 50 frames of our simulation because our output frame 1 is actually looking at frame 50 in the input. So you can see frame 1 is no longer starting at the very rest position here. So it's up to you if you want to disable the retime when you're experimenting with these settings or not, but I'm just going to leave that as is and do a new flipbook of our updated and time-warped curve simulation. So now in this updated sim, it looks like a lot of the collision issues are fixed. It does look like the actual behavior of the sim is not quite as nice as it was before. So I think I'm going to revert the substeps back to 5 to preserve the behavior that we were already getting. And as you can see, this is a time-consuming process to experiment with all of these different things and to dial in just the behavior that you're looking for. And don't feel like all of your collisions and such have to be absolutely perfect, because in big finished professional projects, there are always little collision issues and things like that here and there that are really not problematic and nobody's ever going to notice. Of course, we want our work to be as clean as possible, but don't go too crazy trying to make sure every little pixel is perfectly avoiding intersections. And yeah, so this is looking pretty cool. As I said, I'm going to back off on the substeps to kind of preserve the behavior that we were getting before. So once again, back on our Vellum solver, backing off those substeps back to 5. And I'll leave the collision passes at 50 here. And maybe I'll increase the wind force just a bit. Maybe turn that up to 1.3 and see how that looks. And with the collision passes set to 50, but the substeps dialed back down to 5, we're now getting a very nicely behaving and also nice and clean simulation here. I'm not seeing any massive collision issues right now. At least nothing that's obviously very apparent, and the behavior is looking very nice and flowing quite well, and I'm quite happy with this and ready to cache this out. And perhaps this could look cool if we increase the amplitude on the turbulence that we're applying in that volume velocity curl noise. So if you want to update that, you could of course go to this volume velocity here and increase the scale on that curl noise. But it can be a good idea to not try to get this too perfect before you start seeing things in shots. So when you're looking at something in its rest position like this, it's going to read a little bit differently than it actually does when it's flying through space or seen up close and far away. And you really do need to get this into the actual animated shots in order to make your final tweaks. So this is looking cool as it is now. So I'm going to go ahead and cache this out. And because we're doing a time remap on this to slow this down quite a bit. Unlike the soft body version that we weren't time remapping before, we were caching that one out with 2,000 frames here. But in this case, we could actually cache half as many frames because we're doing a time warp and we're actually getting twice as many frames out of this as what we're actually caching. So I'm going to copy the cache for the soft body tentacles, and we're going to put that after our vellum solver for the hair curves and before the time warp. Rename that cache to tentacles hair curves, and of course change the path as well. So that'll be tentacles hair curves v1, and change the file name as well to tentacles hair curves, and start and end for this will be 1 through 1000. And then if we're caching from frames 1 through 1000, then on our retime here, it can make sense to set our input frame range to 1 to 1000 to match that cache. And then the output frame range is going to be 1 through 2000. So as we did earlier, we have our output frame range covering twice the time as our input frame range with this interpolating in between. And now we can run those 1000 frames for this hair curve simulation. Now after caching out the sim and cleaning up the scene a bit, I'm finding that these simulated curves are a bit slower to load and display than I would expect. And there are a couple things that could be contributing to this. First of all, if you look at our file cache, you can see we have lots of unnecessary attributes here. And we did some cleanup on the attributes when we did our soft body simulation and cached that out. We have an attribute rename here that's throwing out all of the point attributes except for velocity and rest, and it's cleaning up primitive and detail attributes as well. And we have a group delete SOP that's deleting all groups. So we can just copy both of those and then go back to our vellum hair curve sim and paste those in just after the solver, just before the cache. And now we have much cleaner results. Before we had 32 point attributes and some other information as well, a few groups. Now we have no groups and just position and velocity. In this case, we actually don't have a rest attribute because we're just referring back to the rest position of the curves before the sim, which is fine. We're not doing any sort of remeshing or anything like we were for the soft bodies. So in this case, I'm not too worried about not caching out rest data. So now we have some more lightweight geometry that we can cache out to disk. And another thing that we could experiment with is caching out BGOs instead of BGO.sc. BGO.sc is a compressed version of BGO. And my understanding is that in some cases BGO can be faster, some cases BGO.sc can be faster. It depends on whether you're more limited by hardware I/O or processing power. In this particular case, I think we might get a speed up by just writing out BGOs instead of the SC format. And if we change this file name to be just writing out BGOs, then we'll need to delete the other files on disk if we want to just overwrite this version of the simulation. Because currently we have all of these BGO.sc files that won't be overwritten with that different file name. So I'm just going to manually delete those and recache our simulation as BGO files to see if that's any faster. In this case, I'm not really worried about the compression because these are just a few curves with only a couple attributes, so it shouldn't be a very heavy cache. For heavier geometry, I might be more concerned about disk space, but I'm not worried about it for these hair curves here. And even though we have to recache out this whole simulation, you can actually see in our timeline here, it looks like we still have the entire simulation all stored in RAM. So in our case, we're lucky and we don't actually need to rerun the simulation itself. We just have to rewrite these files to disk, And because that sim is still stored in RAM, this will be very quick just to write out these new files. Yeah, that was near instant, not just video editing. We now have all 1000 of our BGeo files, and it's still displaying a bit more slowly than I might expect, but at least we know we've done what we can to clean up that geometry so we're not loading a whole bunch of unnecessary data.